Hello, everybody. So we have just finished working on drawing Lewis dot structures. That basically gives you the ability to determine the connectivity, the atom connectivity of a molecule, and just see what it looks like, but only in 2D. So now we're going to take it to the next level, and we're going to look at molecules in 3 dimensions. We're going to look at the shape of molecules. So this first part of this video is going to cover bonding and geometry models. So there are 3 types: VSEPR, valence shell electron pair repulsion theory, valence bond theory, and hybrid orbital theory. And then we're going to talk about polarity. So in this part of the video, we're just going to talk about the VSEPR theory. Okay. The whole basis for molecules having the shape that they do has to do with the fact that atoms and lone pairs, they're made up of electrons, and there is repulsion if they get too close to each other. So the orientation in space, the 3D shape, is to minimize this repulsion. So I want you to think of just a molecule that has some central atom and it has atoms around it, maybe some lone pairs. Each of those atoms and lone pairs is going to take up space. Think of them as a balloon taking up space. So to minimize repulsion, they're going to adopt these shapes. If there are 2 groups, and the center here is the central atom, if there are 2 groups, they're going to get as far away as possible and adopt a linear shape. 3 groups, it looks like a triangle. We call it trigonal planar because that triangle is flat. 4 groups, and again, a group could either be an atom or lone pair. 4 groups is not a flat square. It's actually a tetrahedral shape. 5 groups, you have something that looks more like a trigonal planar shape in the center in what we call an equatorial plane, and then 2 straight up and down in an axial plane. Since it's trigonal in the center, we call that trigonal, and then bipyramidal because you can actually connect these to form what looks like a pyramid. And then the last shape where you have 6 groups, you have 4 in the center. This is now like a flat square, but then 2 straight up and down, and it's an octahedral. So the shape has to do with how many groups are around the central atom. But there's a little bit more detail than that. So you do need to be aware of these sort of electronic groups. Each electronic group could either be an atom or lone pair. It's not the number of bonds. For example, if you had a double bond, it's not 2 groups. That still just represents 1 group, just 1 atom connected there. So 2 groups, I mentioned linear, 3 trigonal planar. This is another view of what these shapes look like. Here's the trigonal bipyramidal, 5 groups. The center dot is the central atom. Here's the octahedral. So your job in determining the shape is to identify the number of electronic groups around the central atom. Each of those needs to take some region of space to give us this orbital geometry. So the orbital geometry is just basically the orbital shapes, the balloon shapes. 2 groups is linear, 3 groups is trigonal planar. Then the shape of the actual molecule depends on whether or not you have lone pairs. So lone pairs take up space and they influence the shape, but to name the shape, we only look at the atoms. Okay, I'm gonna give you an example. Water, H2O. You could draw a Lewis dot structure like this. You need to identify the central atom, it's O. Now count how many electronic groups are around it. You have 1, 2 lone pairs, and then 2 atoms. So you have a total of 4 electronic groups. So you need 4 balloons for the 2 lone pairs to go in and for you to bond 2 hydrogens. So if you go back, you remember, oh, 4 groups is tetrahedral. Great. That's the orbital geometry that holds all of those electronic groups, lone pairs and atoms. But if we want to name the shape of water, because it has lone pairs, we don't call it tetrahedral. We kind of erase the lone pairs, so to speak, and you look at what's left. And what you have is this bent shape. So we call it bent. Sometimes you'll see it referred to as a V shape. So again, we cannot call water a tetrahedral shape. It has a tetrahedral orbital geometry, the balloon shape for the lone pairs, but the shape itself with the lone pairs in place and just looking at the atoms, it's bent. Be very, very careful. Beware. You may have drawn, for example, a Lewis dot structure that looks like this and try to determine the shape. If you're not careful, you're going to look at this and think it's linear. But it's up to you to just take a step back, count how many electronic groups around O, then you get to this kind of tetrahedral orbital arrangement, and then you see what the shape looks like at the end. So don't let how you happen to have drawn the Lewis dot structure throw you off and fool you into thinking you know what the shape is. So anytime you do the shape, do the Lewis dot structure, figure out the electronic groups, and then you could draw what the shape looks like, for example, tetrahedron, and then only look at the atoms to determine what the shape is. Let's go through some examples. Here is a linear molecule, beryllium with 2 hydrogens, also carbon dioxide. It's because there are no lone pairs around the central atom and 2 groups or 2 atoms. Linear, as far apart as possible, both 180-degree bond angle. You do need to know these bond angles. When you get to electronic groups equals 3, getting as far apart as possible is 120 degrees apart. That's trigonal planar. So if there are no lone pairs on the central atom, the orbital geometry, which is trigonal planar, is the same as the shape. But what if we look at ozone? You guys are aware that there are 2 resonant structures which represent, if you think about a hybrid between those 2 is the actual molecule, but you get this. The central atom is O with 1 lone pair and 2 O's, so you have a total of 3 groups, but you basically cover up the lone pairs. You need the lone pairs to dictate the overall shape, but then when you cover them up and see what's left, looking at the atoms, that looks bent or V-shaped. So that's your strategy. Let's do electronic groups 4. This is methane. It has 4 groups. So right there, I know 4 groups, no lone pairs, bam, tetrahedral. This is how you're going to draw it. It's very hard to draw 3 dimensions for these molecules. So the way you draw a tetrahedron is a line flat, straight up, and then 1 down off to the side. And then this molecule's in 3D. So this hydrogen here is going back behind the screen. So I give it a dash to make it look far away behind the screen, and then a wedge forward. So these are both on the same side, on the right side. So don't put a dash and a wedge across from each other. That doesn't work. They have to be right next to each other. And it just means one is coming towards you and one is going away from you. I recommend getting a cheap model set or just playing around with maybe an eraser and toothpicks and try to visualize the tetrahedron. Before I go on, the bond angles are all identical. This is actually a perfectly symmetric molecule. The bond angles are 109.5 degrees. I'm okay with you knowing 109 degrees. When you get to ammonia, that has a lone pair and 3 H's. So it falls under electronic groups 4, but one of them's a lone pair. So if you cover this up and see what's left, you have what looks like a triangle, but it's more a pyramid. So we call it trigonal pyramidal. The bond angle is slightly less than 109 because the lone pair actually takes up more space than an atom, so it pushes these down, these NH bonds down a little more, so it's a smaller bond angle. And water, we already went over, bent, and it has an even smaller bond angle. I don't need you to know these exact bond angles, but something less than 109. You could put like a less than sign, 109 would be sufficient. The most important thing for you to know is the number of electronic groups 2 through 4. But I'm going to show you also groups 5 and 6. So this is trigonal bipyramidal. This is the equatorial plane, trigonal planar in the equatorial plane, and then 2 straight up in the axial. So these guys, if you drew it in 3D, they're 2 straight up axial, 1 across equatorial, and then these are in the equatorial plane. That's hard to draw flat, so we dash a fluorine and wedge a fluorine forward. Since there are no lone pairs around the phosphorus, we would call that shape also trigonal bipyramidal. One lone pair will go in the equatorial plane because lone pairs take up more space, and there's more space in the equatorial plane because they're 120 degrees apart instead of 90. So we actually get what's called a seesaw. So if you take this and put it flat, well, just knock it to the right side so these fluorines are like on the floor. Basically, it's a seesaw going back and forth. 2 lone pairs, you get a T-shaped. 3 lone pairs in the equatorial, look what's left. If you just look at the atoms, it's linear. Electronic group 6, octahedral. 1 lone pair, you get basically a square here, but a group up top, so you could actually connect the bonds and see that it looks like a pyramid. So we call it square pyramidal. 2 lone pairs, we'll put them on the top and bottom, and you get a flat square. So we call that square planar. Okay, the most important thing again is learning the steric number means the number of electronic groups. Numbers 2 through 4 are the most important: linear, trigonal, planar, tetrahedral, and then what the shapes are if you have lone pairs. Okay, that's actually all I wanted to do for VSEPR theory. Your next video is going to talk about the other bonding theories.